Hi class, this is an example problem for unit 4.2 in which we talk about how to find a moment of a force in 3 dimensions. So I've taken problem 4-41 from the 13th edition of the book, and the diagram for that looks something like this, where basically we have this pipe and there's a force acting at the tip of it. So I've redrawn that best of my ability over here. So we have the dimensions all laid out, and this force acting at the end, it has a magnitude of 80 newtons, and we're given the azimuth and elevation angle, which I've drawn for you here. And what we're asked to find is the moment about point A caused by this force. Now in 2D, it was easy enough to just look at forces and distances and say, oh, those are, we take the x distance and the y force, and that causes a moment, and it's going to be positive or negative. In 3D, it's rarely that's really the best way to go about it. It's really hard to break everything down into perpendicular forces and distances and multiply them and keep track of, is that positive or negative, which way is it going? It gets hard to use the right hand rule to know if things should be positive or negative. So instead, what we typically use is the cross product. The cross product, if you set it up correctly, will always give you the right signs. It'll give you the right magnitudes for all your different directions, right? Because now our moments, we're going to be finding moment vectors, which means the moment isn't going to just be sticking on the board. It's going to be sticking out at some angle with an x, y, and z component. So when we find the moment using the cross product, the equation looks like this. We're going to find that the moment about point A is equal to, and it's always got to be the position vector, and that position vector needs to point from the axis of rotation, in this case point A, to the line of action of the force, where the force is acting, which in this case is point C out here. So the position vector first crossed with the force vector. If you flip those, your signs will be the opposite of what they should be. And if you flip the direction that the position vector is pointing, your signs will be the opposite of where they should be. So always know position vector first, and it goes from the line of from the axis of rotation to the line of action of the force. Can't tell you how many times my statics teacher made us repeat that when I took this class. And then the force vector. So that's the equation we're going to be coming back to. First, we need to find what these are. So let's start with the position vector. This one's easy enough. As we've talked about before, with position vectors, you're the GPS and you're telling it how to get from point A to point C, but it can only go in your cardinal directions, X, Y, Z, right? Just like your GPS tells you to go this far north and then that far west. In this case, we're telling you to go this far in the X, this far in the Y, this far in the Z. So we're telling somebody how to get from A to C. First, we're going to tell them you're going to go, let's start in the X. So in the X, you're going to go plus 300 plus 250 millimeters. So that is going to be 550 in the X direction. Then I'm going to tell them how far in the Y direction they got to go. They got to go 400 millimeters in the Y direction. And then they got to go minus 200 in the Z direction. And so we'll keep track of that. And now that force, we got to revisit unit 2. We remember how to use an azimuth and elevation. So the force, the x component is going to be the magnitude times cosine 30 times, and this one's going to be the x distance, so it's times sine 40. Because we want that opposite edge of this upper triangle. And that will be in the positive x direction. And then y, same general idea, 80 cosine 30 cosine 40 And it's also going to be in the positive direction. And then z is it's going to be in the negative direction, so it's going to be 80 minus 80 sine. All right. So next we gotta plug in these two equations. So 2 and 3, we're gonna stick them into 1. And now we gotta set up our cross product. So the moment infinite equal. And so this is how we're gonna do it. We have basically setting up like a 3x3 sort of matrix looking thing. So we have I, J, K in the top row. And then we're gonna have the X, Y, and Z components of our position vectors. So 550, 450, minus 200. And then we're going to plug in the values for our force vector. I didn't simplify this down, but if I did, it would be 44.53, 53.07, and minus 40. Okay. So now comes the fun part. If you have a fancy calculator, or if you use Excel as a calculator, they have newer calculators will have, and Excel have cross product calculators where you can just feed them your two vectors and it'll do the math for you. But if you're a purist and a hardcore mathematician, it's worth knowing at least how to solve a cross product by hand. So when we solve this by hand, what we end up getting, the cross product always yields a vector answer. So the X component, what we do is I'm going to cover up a column with the I in it. I'm going to multiply 450 here by negative 40 here. And then I'm going to subtract the product of 53.07 and minus 200. So we kind of do this X pattern where we go, these multiply by each other minus these multiply by each other. So that gets me 450 times negative 40 minus 53.07 times minus 200. That's my I. Now my with the J's, I'm going to start out with a negative in front. The J, just throw in this negative. So I'm going to cover and do the same thing with the J column. And I'm going to take this 550 here, multiply it by this negative 40 here, and I'm going to subtract the product of 44.53 as minus 200. So same thing. Broke with the sort of X pattern. So I get 550 times minus 40 minus 44.53 times minus 200. And all of that gives me my Y component. And finally, I'll do my Z for K. So this one, I'm plus again. And I'm going to do the same thing. I cover up my K column. I'm going to go boink, boink, just like we've done every other time. So we get 550 times 53.07 minus 44.53 times 450. So now I got X, Y, and Z components. I can simplify them out a little bit, and I get that my moment vector is minus 5,386 in the X direction plus 13,094 in the Y direction and plus 11,376.5 in the Z direction. And my units here are Newton millimeters. And that is the vector answer. Now they may ask you for the magnitude in which case we just take square root of the sum of the squares, and we just do it over here real fast. So the magnitude of that, just like the magnitude of a force, just take the square root of some of those squares. And get your magnitude. And the magnitude overall is 18,162.8 Newton millimeters. And that is the answer. So yeah, that's all there is to the cross product. It's a little bit daunting to solve at first, but if set up correctly, and if you're just very careful to make sure that you don't lose track of signs anywhere, it's really easy if you aren't kind of explicit writing it out to accidentally drop one of these negative signs and mess it up. But it is nice. It gives you the vector answer. It takes care of the signs for you as long as you set it up like we discussed. So that is solving for moments in 3D and the cross product.